So, welcome to this lecture. So, in the last few lectures, we studied the topological property of being connected and path connected. And saw several examples. So, two examples which we did not see were, so the problems of whether SON, UN are connected or path connected will be pending, will be taken up later. So, we need to develop a few more tools before we can answer the question of whether SON and UN are path connected. So, however, for the next few lectures, we will study the property of being compact. Okay, so let's begin with the definition of a Hausdorff topological space. So let X be a topological space. Okay, so we say that X is Hausdorff if for points x1, distinct points x1 and x2 in X. So, we have our X, we have x1 here and we have x2 here. So, there should be two small open sets which contain x1 and x2 which are disjoint, right. So, we can take any two distinct points x1 and x2 and there exist open sets u1 and u2 such that x1 belongs to u1, x2 belongs to u2 and u1 intersection u2 is empty and u1 and u2 are disjoint. If this happens for all pairs of distinct points x1 and x2, then we say X is Hausdorff. Okay, so here are some easy exercises. Okay, if X and Y are Hausdorff, then the product with the product topology is Hausdorff. So, let us see how to do this. So let us say we have 2 points x1, y1 and x2, y2. Okay. So, now since x1, y1 is not equal to x2, y2, so this implies either y1 is not equal to y2, or x1 is not equal to x2. Okay, so let's simply assume that. So let's assume that y1 is not equal to y2, right? So then our y1 is here. I'm sorry, y1 is here and y2 is here. So since y is Hausdorff, this implies there exists open sets such that y1 belongs to v1, y2 belongs to v2, and v1 intersection v2 is empty, right? So this is our v2, this could be our v1, right? So then we know that, so then x cross v1 and x cross v2 are open sets in the product topology x cross y, right? So this is x cross v2 and this is x cross v1, right? So clearly x1 comma y1 is in x cross v1, x2 comma y2 is in x cross v2, and the intersection is empty, right? So this shows that x cross y is Hausdorff. Okay, so in the same way we can easily check that if xi for I in I is a family of topological spaces, of Hausdorff topological spaces, then the product so obviously every time we talk of the product as a set, we are giving it the product topology is Hausdorff. Okay, and imitate the proof of 1. The same proof as in the previous case will work, and I will leave it as an exercise. So finally, the third easy example or easy exercise is X is Hausdorff and Y contained in X is a subspace. Then Y is Hausdorff. Right? So let's quickly see this. So suppose this is our X and let's say Y is this. Yeah? So if you take any Y1 and Y2, then since X is Hausdorff, there is an open set U1 containing Y1, U2 containing Y2 such that U1 intersection U2 is empty. Right? So then clearly U1 intersection Y contains Y1, U2 intersection Y contains Y2, and these are disjoint open subsets of Y, right? Thus Y is Hausdorff. Okay, so The above exercises give us plenty of examples of Hausdorff topological spaces. So we are mostly interested in Hausdorff topological spaces, and we will almost deal exclusively with Hausdorff topological spaces for the rest of this course. Yeah. So for the rest of this course, we will be interested only in Hausdorff topological spaces. So if nothing is mentioned, then it's safe to assume that the topological space we are working with is Hausdorff. Okay, so we have defined what Hausdorff means. So now we are ready to define compactness. Okay, so let X be a Hausdorff topological space. Okay, so we shall say that X is compact if the following happens. So every open cover Ui, I in I. So what do we mean by an open cover? It means each Ui, we are given a family of open sets Ui, and the union of all of them is equal to X. Yeah. So we are given any open cover, and given any open cover has a finite subcover. That is, there exist finitely many indices I1, I2 up to In such that X can actually be covered by these finitely many open subsets. Okay, Uij, sorry. So let's see an example of a topological space which is not Hausdorff. I'm sorry, which is not compact. So example, R is not compact. Okay. So to say that R is not compact, it is enough to produce an open cover for R which has no finite subcover. Yeah. So that's easy. So what we do is we take any n plus 1, and we take n minus 1 by 4 and n plus 1 plus 1 by 4. Right. So then we can write R as the union over n in integers, n minus 1 by 4 and n plus 1 by 4. Right. So clearly if we take any finite subset, so clearly any finite subcollection in this union, it will not cover R. Any finite subcollection of intervals of the type n minus 1 by 4 comma n plus 1 plus 1 by 4 will not cover R. Right? So thus, this cover has no finite subcover. Thus, R is not compact. Right? Okay. And exactly, so R is not compact. So now we want to construct some very basic examples of compact spaces and prove some very basic results about compact spaces, which is exactly the same as we did when we talked about connectedness. So the first result we are going to prove is the interval 0, 1 is compact. So the proof is very similar to how we proved that 0, 1 is connected. So let's prove this. So suppose we are given an open cover, we are writing UI be an open cover. So our aim is to find a finite subcover of this. So we need to show that. This has a finite subcover. Okay. So as before, we let S be equal to those x in 0, 1 such that this, when we look at this interval, the closed interval 0, x is covered by finitely many ui's. Okay. So clearly 0 belongs to S, right? So for 0 to belong to S, what we need is 0, comma 0. This is just the single set 0 is covered by one ui, right? So we can just take any ui naught which contains 0 or any uj, let's say, any uj which contains 0, and then obviously this interval, which is just this 0, is contained in this uj, right? Okay. So when I say covered by finitely many ui's, I mean that this interval 0x is contained in finitely many ui's. Union of finite union of ui's. Okay, yeah. So let x naught be equal to supremum of x in S x. Yeah. So we claim that x naught is also in S. So let us prove this. So there is a sequence xn's converging to x naught with xn's in S, right? So let x naught be in some open set. So we have 0, we have 1, and let's say our x naught is here. So x naught is going to be in some open set ui naught. Okay. So there is an epsilon positive such that b epsilon x naught intersected with 0, 1 is contained in ui naught. Yeah. Okay. So and since these xn's are converging to x naught, all but finitely many xn's are in this interval So, all these xn's, eventually all of them will land inside this small open neighborhood around x naught. Okay. So, we choose some xm in p epsilon x naught intersected with 0 1. Right. So, this 0, this is x naught, this is our interval, and let us say xm is here, let us say this is 1. Yeah. So, then as xm is in S, this implies 0 comma xm is covered by, or let us say is contained in a finite union of ui's. In a finite union of ui's, right. And moreover, we also know that this interval, moreover, this interval xm comma x naught is contained in p epsilon x naught intersected 0 1, which is contained in this ui naught. So, this implies that 0 comma x naught, which is equal to 0 comma xm union xm comma x naught, which is contained in 0 comma xm union ui naught, right. Now, this interval 0 comma xm is contained in a finite union, and therefore 0 comma x naught is contained in that finite union along with ui naught, which is therefore also going to be finite. So, therefore, we conclude that 0 comma x naught is contained in a finite union of the ui's. Yeah. So, thus x naught is in S. Okay. So, this proves our claim. The claim that x naught is in S. Yeah. So, now next we claim that, x naught is equal to 1. Yeah. So, once again, if x naught is strictly less than 1, then that would mean that there is some, so let me just make the picture here once again, and this is our epsilon and this is our xm. That would mean that there is some epsilon positive such that x naught comma x naught plus epsilon is contained in ui naught, right. So, again, so this implies that 0 comma x naught plus epsilon, which we can write as 0 comma xm union x, this x naught plus epsilon, is contained in a finite union of the ui, right. So, this implies that x naught plus epsilon belongs to S, which contradicts the assumption that x naught was the supremum. Right. So, thus x naught has to be 1, x naught cannot be strictly less than 1, right. So, since x naught is equal to 1, this implies that the 0 comma 1, we have already seen that x naught is in S. So, therefore, this implies that 0 comma 1 is contained in a finite union of the ui's, right. So, thus there is a finite subcover is contained in j equal to 1 to n some uij, this implies that so therefore this open cover, so this proves that the open cover we started with has a finite subcover. Thus, this interval is compact. So this completes the proof of the theorem. So we will end this lecture here.